We now begin a new section of notes that introduces a very, very powerful technique for understanding how control systems work. How is it that they're able to move poles using feedback, and where do those poles really go? And what kind of authority do I have when I design a controller to make the poles go where I want them to go? This technique is called root locus plots, and this chapter looks at how do we analyze control system design and so forth using the root locus plot, and how do we make a root locus plot is one of the primary goals of this chapter. And then in the next chapter of notes, we will look more at how do we make a control system design using what we've learned in this chapter about the root locus and how it works and things like that. We've actually seen root locus plots before where we've made them manually in a kind of a brute force fashion. What we're going to learn in this chapter is different. It has to do with techniques for very, very quickly sketching what a root locus would look like for some system, and then being able to use that information later on in a control design. So let's get started. We're going to look at manually making these root locus plots. And the reason for it, if you go back a couple of chapters, we looked at dynamic responsive systems and then at the desired dynamic responsive systems. And we saw that when we were looking at dynamic response, that the transfer function pole locations determine the performance characteristics that you're going to see. They determine the rise time, the settling time, and the overshoot of the system, for example. And so if we have some desired rise time, settling time, and overshoot, we also saw that that meant something about where the poles of the closed loop system had to be. And since feedback can change pole locations, we have some ability to then achieve these specifications by using feedback in a design. So what we're going to look at here is we're going to assume that we have a single design parameter that we can vary, so a single variable design parameter in our control system, and our goal is going to be to select the value of that design variable, maybe some number from 0 to infinity or just any real number. What value for that parameter would be the best one to select, or what range of values would be acceptable. And so thinking about it, we could choose different representative values. So suppose it's k is the thing we want to select, and we could say, well, I'm going to try k equals 0 or 1 or 2 or 10. I could select representative values, and I could plug it into the closed loop transfer function. I could solve for the poles of the closed loop transfer function for each value of k. I could look at where those end up on the S-plane, and if I'm really lucky, I'll find a value of k that gives me acceptable closed-loop pole locations. Or maybe I could automate this somehow. If I'm clever with MATLAB and I can write some script that cycles through values of k in a certain range and plots the pole locations for each value, and then I could select the poles that I prefer, and then find the value of k that gives me those poles, and that's my design. That's kind of the idea, except we're not going to go about it in quite such an ad hoc fashion. After we get started, we'll look at some examples of doing things very, very manually, brute force, but after we do that, we're going to find techniques for drawing these plots of the closed-loop pole locations that we can do very, very quickly with very, very little hand calculation, just drawing stuff on an S-plane, and that's really, really valuable. It's kind of a back-of-the-napkin kind of thing that you can do. You're sitting at a restaurant with your friends, and you're designing a controller, and you don't have MATLAB handy, and you can just whip out your napkin and draw where the poles are going to go. It's going to be just like that. So poles, we know, are the roots of the denominator of the transfer function. The denominator of the transfer function is the characteristic polynomial, and poles are the roots of this, so that's part of the reason for calling it a root locus, because we're drawing where poles go. And since we're drawing all of the possible sets of locations, which is a locus, these plots are called a root locus. And they were made originally by someone named Evans, so once in a while you will see them called an Evans root locus plot. That's what we're going to learn about. The root locus is a parametric plot versus some design parameter k of the roots of some equation. 1 plus k of b of s over a of s equals 0, or I could multiply both sides of that equation by a of s, and I get then that a of s plus k times b of s equals 0. That is, in fact, what a root locus plot is in its most basic fundamental statement, but we can apply that to control systems to get a specific understanding, especially if we focus on the unity feedback case. By the way, before I get to that, when I say it's a parametric plot, what that means is that I'm going to draw an S-plane, and I'm going to draw where certain poles go. And we've seen root locus plots that have poles that start there, and one goes up and one goes down. Something like that. That's an example of a root locus plot. A parametric plot is one where you can see the pathway that the pole will take, but you can't directly from the plot infer the value of k that put them there. That would be different. You could imagine a different kind of plot that was like real of all the poles. And this here was k, and then I've got one pole that does that and one pole that does that. And you can imagine a plot that looked like that. That's not a parametric plot. And in fact, that's a little bit harder to use because it's harder to see what the combination really means than if I look at something like this. So anyway, the plots that we have are going to look like this. And this is the imaginary axis, that's the real axis, and we're going to show where poles can be as k varies, and then we'll have another way of figuring out what value of k achieved a certain set of pole locations. So this is what root locus can do. It can plot all of the roots of equations that look like that. All of the values of s that satisfy that, as long as a of s and b of s are polynomials in s. And the reason that's useful for a control case is that if I have a unity feedback situation, which is quite a common configuration for control, we know that the transfer function of this closed loop is t of s equals k times g of s over 1 plus k times g of s. I'm interested in what are the roots of the denominator of this equation, so I want to know when does 1 plus k times g of s equal 0, or what values of s does 1 plus k times g of s equal 0? That's where the poles are. And if you compare that to this, that looks a lot like this if I can write g of s as a numerator polynomial divided by a denominator polynomial. Or it looks like this if I just multiply top and bottom of the equation by the denominator polynomial. So if we have a unity feedback configuration, which is very common, then this closed loop transfer function is already written in a way where I'm trying to solve for these roots, 1 plus k times g of s equals 0, and if my plant has the right form, and then these root locus rules apply. There are some constraints on this, and the constraint is that g of s is a rational polynomial, as we've said, so it's a numerator divided by a denominator polynomial in s. The numerator could be factored into a product of s minus the first 0, s minus the second 0, and so forth, and the denominator can also be factored that way. That's not too surprising. We've done that quite a lot. But one thing that is new here is, for the purpose of this chapter for how we present the material, we are going to assume that the polynomials are monic. What monic means is at the highest order. So if I wrote this, multiplied this out and wrote this out, the highest order would be s to the m plus some b1 s to the m minus 1 plus etc. And here, if I wrote that out, it would be s to the n because of the m and n's here, plus dot dot dot. Monic means that it's 1 times. The highest order of s is exactly 1. So is this a limitation? Well, if I had, I don't know, 5 times s plus 2 over 3 times s plus 1, neither one of those is monic. But I can always make one of them monic by absorbing the constant into the other. So I could say, well, that's 5/3 s plus 2 over s plus 1. Well, now my denominator is monic, but my numerator is not. But what we do in that case is we say, well, what I really want to do is I want to plot the roots of 1 plus k times 5/3 s plus 1 over, s plus 2, s plus 1. And I will think about all of that together as some new k new. I will absorb that constant into k, and that allows me to have my monic b of s and my monic a of s. And that's what we're going to do. The only time this becomes at all tricky is if that constant is negative. We will see that is going to invoke a different set of root locus plotting rules. We'll have one set of rules if the constant, this overall constant k nu is positive, a different set if that overall constant is negative. And so if that number that I'm absorbing into k is itself negative, I have to remember to use the other set of rules because k nu becomes negative then. So those are the assumptions we make. We have monic polynomials, and we can see that we can do that quite generally. So Zi are the zeros of the open loop transfer function. Pi are the zeros of the open loop transfer function. And this is stated in bold because what we're going to do here in this chapter is we are going to use information from the open loop transfer function to give us directly information about the closed loop transfer function if I have a unity feedback configuration. This is not the first time we've done that. At least one other time, when we were looking at steady state error with respect to different kinds of inputs, we said if I have a unity feedback situation, then I look at the open loop transfer function, I look at the number of poles there are at s equals 0 in the open loop transfer function, and that tells me what the system type is. So from the open loop transfer function, in that case, I inferred something about the closed loop performance, the closed loop transfer function, what the system type would be. The big exception to this, almost everything we develop in this course is geared toward using open loop information to tell me something about closed loop performance. The big exception is the Routh test that we just did in the last chapter, where we had to actually compute the closed loop transfer function to do the Routh test. There was no open loop shortcut for that. So if these are the open loop poles and zeros, then I'm looking for where are the closed loop poles, and we know that they're the roots of 1 plus kg of s equals 0, or a of s plus k times b of s equals 0. And especially looking at this form, I think it's the second form, it's pretty clear that if I were to factor any old polynomial with that k that's multiplying some part of it and not some other part of it, that the roots of that equation are going to depend on k. So the feedback does, in fact, move poles of the closed loop transfer function. Zeros aren't. Zeros are not affected by feedback. If you look at the transfer function, I've got k times b of s over a of s divided by 1 plus k times b of s over a of s. That's my closed loop transfer function. Multiply top and bottom by a, and that equals k times b of s over a of s plus k times b of s. So the closed loop poles are the roots of the denominator, which have a k in them. The closed loop zeros are the roots of this equation, but you see that k is multiplying all of that, and so I can factor that out. If k times b of s equals 0, then I could divide both sides by k, and I get b of s equals 0, which is just what I started with. That's the same zeros as the open loop transfer function. So feedback does not move zeros, but it does move poles. We're going to start with something that's not too different from what we've seen before. We're going to find a root locus manually, just to be reminded of what a root locus plot looks like and how we might be interested in using it. And then we're going to move on to finding more efficient ways, more clever ways of plotting a root locus like this one by hand. So the example is g of s is 1 over s times s plus 2. This is our open loop transfer function. I'm assuming a unity feedback configuration, and I want to find where the poles of the closed loop system go as I move the gain k. So a of s is denominator, it's s times s plus 2. B of s is numerator, it's just 1. And the locus of the roots we said was, okay, it's a of s plus k times b of s equals 0, which is s times s plus 2 plus k times 1 equals 0, which is what we have here. And multiplying out, I get s squared plus 2s plus k equals 0. And we can apply the Routh test stability criteria for this, and we remember that for a quadratic, we have the stability when all of the coefficients are positive. So here, as long as k is strictly positive, I have a stable closed loop system, even though the open loop system has an integrator at the origin, a pole at s equals 0, an integrator. The open loop system is not stable, but the closed loop system is. In this case, because it's a quadratic, we can solve for the roots of that equation using quadratic equation. So if that is my quadratic A, quadratic B, quadratic C, the roots are at minus b, minus 2 plus minus square root of b squared, minus 4ac, all divided by 2a, and all of that works there. I can factor this 2 and that 2, that gives me a 1, and the 2 can come inside the square root where it divides stuff by 4. And I get minus 1 plus or minus 1 minus k are the two root locations as a function of k. And looking at that, if k is between 0 and 1, the square root then is also between 0 and 1. And so I'm going to have minus 1 plus or minus 0 all the way up to minus 1 plus or minus 1. So I'm going to have the real axis between minus 2 and 0 completely filled up. When k equals 0, we see that I've got minus 1 plus or minus 1, so that's minus 2 and 0. So when k equals 0, I've got a pole at minus 2 and a pole at 0, the origin. When k is bigger than 0, these poles are moving. That pole moves that way, and that pole moves that way. And when k is exactly equal to 1, I have minus 1 plus or minus 0. So when k equals 1, I've got two poles right on top of each other right there. When k is bigger than 1, that square root, the inside of the square root, becomes negative, and so the square root itself becomes imaginary. And I have minus 1 plus or minus some imaginary number, or overall is complex. So I've got one pole that goes up, I've got one pole that goes down. The real part is -1, and the imaginary part is the square root of 1 minus k. So in conclusion, the roots are real and negative for k between 0 and 1. The roots are complex conjugates for k bigger than 1. And we've seen root locus plots like this before, and we're going to see root locus plots that are quite a bit more complicated than this. But this is an example that we can do by hand, which most often we can't, but in this case we can. And we can see all of the possible pole locations as k changes. If I want poles there and there, I can't do it. Not with this system. I'd have to somehow change the way I'm building that feedback controller. I could not use simply a proportional controller. I'd have to do something more fancy than that. It's possible to do, but not with this controller. I'm limited in this controller to have poles that are somewhere on that locus. So suppose I have a design parameter that says I want a damping ratio of 0.707, which is 1 over square root of 2. And we can look at the equation in standard form and say, well, the standard form is s squared plus 2 zeta omega ns plus omega n squared. And we know that our roots of the equation, our denominator is this. So if I make a correspondence, yes, those agree. And these here have to agree. So 2 times square root of 0.707 is 2 over root 2 times omega n s equals 2s. So that tells me that omega n must be 1 over root 2. Must be root 2. And if that is the case, then omega n squared must be 2. And so I have this correspondence right there, k equals 2. So I could have figured it out by the equations that I could get that damping ratio, or I could remember that a damping ratio of 0.707 has a geometry to it where the poles are at a 45-degree angle from the imaginary axis, plus minus 45 degrees. And so I'm going to have a location on the axis where the real part of the poles, on the locus, where the real part equals the imaginary part. So if I look at this equation here, I see that the absolute value of -1 is in fact 1. And if I have k equals to 2, I would have 1 minus 2 inside of the radical, which is -1. Square root of -1 is plus minus j. And the absolute value of plus minus j is also 1. So that gives me the other solution there, and both of those work. So in that section here, we've looked at just a brief introduction reminding us what a root locus is, showing again how to plot one manually by brute force. But next we're going to start learning some rules for how to plot them without brute force.